Ladies and gentlemen, today we're going to talk about gas laws and something you need to be aware of, that we're going to go through this relatively fast. So make sure you take notes. All right, I'm going to change my pen color to magenta, or this purple color, and here we go. So when we're looking at gas laws, we're talking about the set of equations that explains the property of gases, how pressure, temperature, and volume all change. So these are the four variables we're looking for. Pressure, P, is temperature, pressure either in atmospheres or torr. Torr, and I'll put off to the side here, 1 atm is equal to 760 torr. And in chemistry, these are the two values that we use. Temperature is in Kelvin, not degrees Celsius or Fahrenheit. So we must have it in Kelvin. Kelvin is the absolute temperature scale, starting with 0 all the way up to infinity. There is no negative temperatures, and we'll explain that in the book. V is a volume, liters. N is amount in moles. So we're looking at how these things how gases, how changing one or two of these can affect everything else. Now what I'm going to do is go back and forth between this slideshow and a simulation so I can explain to you why this occurs. So when we're looking at the first one, this is easy. This is called Boyle's. This is found by Boyle. And basically pressure is related to inverse of volume. If the pressure goes up, volume must decrease. Or if volume increases, pressure must decrease. So what we have is we have these relationships. This little sign here means proportional to. And this is just a constant. And this is based on the experiment. This is a system constant. It can mean anything. So we're going to talk about what we call the gas constant a little bit later. And so what we have is that we can set this relationship up and say if we know the pressure and volume at the beginning of an experiment, P1, V1, it can actually equal to the pressure and volume after the experiment, P2 or V2. Because remember, P1 is equal to a constant. If we change pressure, volume must change to keep this system constant. And this is what we have. Now, what we need to do is keep the other two values constant, keeping T and N constant. Now, I'm going to quit this and show you what we mean. So, we're looking at pressure and temperature. Pressure and volume, excuse me. So what I'm going to do is add some molecules of light particles. We're going to change hold pressure constant, temperature constant, and we're also going to keep the number of atoms constant, but we're not going to touch this little bicycle pump. Now, if you notice that the pressure is range about 5.1, it goes back up and down. We'll probably keep this a little bit more constant. We added 50 more molecules to know the pressure goes up. But what happens if we change the volume? So what we're looking at wall collisions, we're keeping temperature and N constant. So at N is around, say, 10.9 atmospheres pressure. Look how many wall collisions, 166. Now we're going to move this volume about halfway. Look what happens to the pressure. It increases. Let's look at the number of wall collisions. That's going to increase as well. So what we're seeing is that the pressure is dependent upon the number of wall collisions. That's how we measure pressure in the simulation. And that makes sense. If you got a balloon, what keeps the balloon out is the tremendous amount of gas molecules hitting the side of the balloon. Now if we change the volume, we're going to notice pressure decreases and the number of wall collisions should decrease as well. And this is kinetic molecular theory at its finest. Now I'm going to go to the next slide, and we have a relationship between pressure and temperature, and it's directly related. As the pressure goes up, the temperature must go up, or vice versa. And when we try and set that to a constant, P1 over T1 is equal to K. And so, whoops, didn't mean to do that. Let's get back to pen. So what we have is this. When we relate to beginning, what we start with and what we end, is that the ratio of P1 to T1 is equal to the ratio of P2 to T2. And that's for every experiment. This is for individual experiment. And that for each experiment, it could be, the ratio can be different. But if we do an experiment, and I can't spell, this ratio would be the same. So what happens when we increase the temperature, we should see the increase in the amount of, whoops, didn't need to do that. Get back in the amount of wall collisions. So we're going to keep volume constant. Let's start off with 50. And we'll increase the temperature. So at this point, the number of wall collisions is 81. Let's increase the temperature. As we increase the temperature, the pressure also increases. If we look at the number of wall collisions, according to kinetic molecular theory, we should see an increase in the number of wall collisions, and we do. So this is why the pressure increases when the temperature increases. Those molecules are going faster, hitting the wall faster. So the actual speed, if we cool it down, the gas molecules decrease in speed. They're not hitting the sides of the wall as fast. So this is what we mean by the pressure-temperature relationship. Now, when we look at the relationship between pressure and amount, we're keeping temperature and volume constant. You notice that if we add more N, we're going to see more P. If we take away N, P should decrease. And therefore, we have this relationship, P1 over N1 is equal to K. If we have beginning and end, this relationship should work for each experiment. So come to this, we're keeping temperature and volume constant. We're going to move that temperature up to about 275 or 250. All right, so look what happens when we add more pressure. Add more N, the pressure increases. If we decrease, pressure should decrease as well. Don't regard this. This is the problem with the simulation. Excuse me. I'm going to stop this and come back here. Next is looking at volume and temperature. Again, this is a direct relationship between volume and temperature. So the ratio of volume to temperature is equal to a constant. Again, this is experimentally. So V1 over T1 is equal to V2 over T2, initial and end. So remember, anything that ends in a 1 anything that ends in a 1 is at the start. Anything that ends in a 2 is at the end. So we don't care what happens in the middle. The ratio at the beginning is equal to the ratio at the end. And here, we're keeping P and N constant. And this is going to be important because the problems you're going to get may not say anything about pressure and N, so you're going to assume that they're going to be constant. If something's going to change, we will tell you. So that's my temperature relation, the volume increases if the temperature increases. Hot air balloons is a good example of this. All right, I'm going to end the show. Come back to here. We're going to keep pressure constant. I'm going to see what happens when we increase the temperature. So increase the temperature, oh, the volume increases. Decrease, the volume decreases. Again, what we're trying, let's take a look at wall collisions. With this volume, the wall collision is 90. Now we're going to heat it up, increase the volume, and the number of wall collisions should remain relatively close. Should be around 90. 89, that's close enough. So this is what happens when we have pressure, keeping pressure and constant. We increase the temperature, the volume is going to increase. Decrease the temperature, the volume will decrease. And we're just playing with all this. All right, next slide. Volume and amount. Blowing up a balloon. I'm not going to talk much about this, but if you add more N, volume will increase. You guys do this every time you blow up a balloon. Increase the amount of gas in the balloon, of air, the volume increases. Now, this is the one that's going to be a little bit difficult. Temperature and amount. So temperature is inversely related to N, meaning that if temperature increases if we decrease N, because this has to be related. So T1 N1 is equal to T2 N2, and we'll keep them P and V constant. And what we're going to do is we're going to try and show this on this. So we're keeping pressure and volume constant. We're going to see what happens when we add the temperature decreases. It went down. Let's add some more. It's going down. Well, we've got to keep the collisions the same. To keep the collisions the same, we're going to have to decrease the amount of the speed of the molecules in order to keep the pressure constant. This is why temperature and the amount it has an inverse relationship. So if we take stuff away to keep the pressure the same, we've got to increase the speed of the molecules. So as we introduce a vacuum, the temperature is going to increase. Now, one last thing we're going to see, and that is algebra review. Everything is based on algebra. Algebra 1, guys. You should be able to do this. Remember, everything is multiplied. To move across the equal sign, you divide, do not add, and make sure you do it correctly. Now, one thing I noticed is that if I go PV is equal to K, everybody struggles with it. It's the same as X times Y equal K. The letters don't matter. It's just variables. You guys can do well with X and Y, but not P and V. And so that's why we're working on this. That's the end of the lecture. Have a nice day, folks.